Hello and welcome. In this lesson, we will cover a machine learning technique that can be seen as a foundation for understanding neural networks. This technique or model is called logistic regression. It is a simple yet very useful technique for solving various classification problems, such as spam detection, diabetes prediction, credit granting, among others. By the end of this lesson, you will be able to implement systems using this technique and the Python programming language. To better understand this type of model, it's important to know how to classify machine learning systems. Machine learning is a subfield of artificial intelligence, and its goal is to develop systems that can learn and improve automatically with data or by obtaining information. We can divide machine learning models into supervised, unsupervised, and reinforcement learning. In supervised models, the system learns from examples. In unsupervised techniques, the system detects patterns by examining data, without these patterns having been presented previously. Finally, in the third class of models, reinforcement learning, the system learns from its actions and the feedback received in terms of rewards. Logistic regression is a supervised learning technique. Supervised models can be divided into classification systems and regression systems. In classification systems, the system attempts to identify the correct class given an input. For example, from a person's financial data, the system attempts to identify whether to lend money or deny the loan. Another example, the system can receive data about a particular animal, and from this data, identify whether it is a mammal, reptile, bird, or amphibian. In the case of regression, the system attempts to output a value from the received data. For example, from receiving financial data, the system can try to predict the inflation rate. It is a technique widely used in the financial market. Despite the name, logistic regression is used for classification. Classification can be binary, where there are only two classes, such as yes or no, positive or negative. And it can also be multi-class, for example, to classify whether a word is a verb, a noun, an adjective, an adverb, and so on. To differentiate logistic regression from linear regression, we can observe the difference graphically, using a two-input or two-dimensional example. This makes visualization easier. In the case of linear regression on a set of points in a plane, we try to fit a line that attempts to capture the distribution trend of the points in the plane. Once this line is fitted, we can use it to predict an axis value from the other. If it is a three-dimensional space, we will try to fit a plane. If it has a larger number of dimensions, we will try to fit a hyperplane. In the case of logistic regression, what we want is to return a decision of the yes or no type or a classification. So drawing a straight line is not enough. Consider this simple example, where a decision needs to be made about whether to lend money to a person based on their salary. Based on previous loan data, it's difficult to fit a line that can answer this question. However, if you use a curve in S-shape as opposed to a straight line, it's easier to make this adjustment. When entering the salary value into the curve function, if the value is closer to the top of the curve, the answer will be yes. Otherwise, it will be no. To transform the line into a curve, it is necessary to introduce a nonlinearity. A commonly used function to introduce this nonlinearity is the logistic function. Hence the name logistic regression. Here we can see the general formula of this function. We would like to highlight the fact that it is a fraction, with the numerator being the number 1 and the denominator being equal to or greater than 1. This means that the value of the function is limited between 0 and 1. In the denominator, we have an exponentiation, based on a mathematical constant called Euler's number, whose value is approximately 2.718. The logistic function is a function with interesting characteristics. First, when placed on a two-dimensional graph, it presents an S-shape. Therefore, it is a function called a sigmoid. The second characteristic is that the values returned by the function are between 0 and 1. This makes it very interesting for binary classifications, where there are two classes to perform the classification, such as yes or no, positive or negative, lends or refuses to lend. The third advantage is that it's a continuous function. This means that at any point on the curve, you can draw a tangent line and calculate the slope of the tangent at that point. This characteristic is used during the model fitting stage, that is, during its learning process. If the model calculates an incorrect value, we can calculate the slope at the point where the error occurred and check the direction in which we should adjust the model to reduce the error. We will see how this is done later. Let's detail how logistic regression works. First, we need a dataset which must be classified. For example, we can receive data from various people to check whether or not we should lend a certain amount of money to them. For example, it could be their salary and the amount of money they are requesting to borrow. In reality, companies use a much larger amount of information to make this type of decision. But for our example, these two pieces of information will be sufficient. Each type of information is called a characteristic or feature. Let's use a dataset about people that has already been pre-classified, indicating whether the loan was granted. They are separated into two groups, one for learning, which will be used to adjust the model, and another that will be used to test the model. At the end of the learning process, and when it passes the tests with a pre-established level of accuracy, then we can say that the system is ready to approve or not new loan requests. Now let's build our logistic regression model. In the first part of the model, we take each input value. In our example, these are the salary value and the loan request value, and we multiply them by a weight and then add a value called bias. The resulting value, let's call it Z. You might be wondering where these weight values and this bias value came from. These values are initially random, and it is these values that will be adjusted during the model's learning phase. They are called system parameters. So what the model learns is what values should be assigned to the weights, and the bias value so that it outputs a correct result. The weights define the importance that should be assigned to each input attribute, and the bias corresponds to a general adjustment of the model. Let's illustrate this calculation with an example. Suppose a person who earns 3,000 wants a loan of 10,000. Suppose also that both peso 1 and peso 2 have a value of 0.01. Let's also assume the value of bias equal to 1. Then, in this case, the value of Z will be 131. This value doesn't tell us much, and what we want to know is whether or not we should lend the money. To do this, we will use the value of Z as input for the sigmoid function in step 2 of the model execution. In the second part, we will use the value as the exponent in the denominator of the sigmoid formula. When we perform the calculation, the final value will be practically 1. This can be interpreted as a suggestion that the loan should be granted. That is, any value equal to or greater than 0.5 can be considered a yes, and below that a no. However, the table with the data indicates that the final value should be 0, meaning the loan should be denied. Therefore, an error occurred, and the model needs to be adjusted to correct this error. This correction is done during the learning process, and we will explain how this step is performed a little later. Now, we would like to explain what was done in a more graphical way. We can view the calculation of logistic regression as a flow. We have the input attributes, which can be seen as a sequence of values x1, x2 up to xn. These values are multiplied by their respective weights w1, w2 up to wn. The results of the multiplication are summed, along with a bias value, generating a value, z. This value is applied to the sigmoid function, represented here by the Greek letter sigma. This function is also called the activation function, and, as we will see later, there are other possible functions besides the sigmoid function. The value generated by the activation function is the value emitted by the network, represented here by the letter y with a circumflex, also called I hat. We use this notation to indicate that it is an estimated or calculated value and to differentiate it from the expected or real value. This model is a metaphor for the functioning of a neuron. A neuron is connected to other neurons by means of filaments called dendrites. Neurons provide inputs to others through electrochemical stimuli. The strength of each stimulus will depend on the strength of each connection, which is equivalent to the role played by weights in logistic regression. In a neuron, if the stimuli received exceed a certain threshold, the neuron fires, emitting an electrochemical signal through its axon, which will be transmitted to other neurons. Because of this similarity, although superficial and not reflecting the complexity of a neuron, logistic regression can be seen as an artificial neuron. And as we will see later, the composition of these neurons in a network forms an artificial neural network. Before we continue, let's talk a little about the notation used in our formulas. When a variable represents a single value, we use a normal lowercase letter. When it represents a vector or matrix, we use a bold lowercase letter. Now that we understand the calculation done by logistic regression, let's describe this step in a slightly more formal way. Given an input vector x with values x1, x2 up to zen, and a weight vector w with values w1, w2 up to when, and a bias value b. Then the linear function z is defined as the multiplication of the transpose of the vector w with the vector x plus the bias. The transpose of a vector is simply the transformation of a vector from column form to row form to facilitate multiplication. It's a transformation that mainly helps in matrix multiplication. The multiplication of two vectors is simply the multiplication of each element, pair by pair, and subsequently the sum of these values, generating a single simple value, also called a scalar. When we apply the logistic function or activation function, sigma, with the value z as an argument, we obtain a value between 0 and 1. Let's look at another example. Given a vector with a salary value of 1, and a loan request with a value of 4, both values in thousands, and let's also have a vector of weights with values 0, 2 and 0.1. Let's also have a bias value of 0.1. In this case, the value of z will be 0.7. Applying the logistic function to this value, we obtain the resulting value of 0.67. This video ends here. Thank you so much for watching. See you in the next video lesson.